In an interconnected world, everybody should talk the same language. So if I draw this length, how long it is. In one part of the world, if some answer comes, then somebody sitting thousands of kilometers away, that person should also understand the very same language. This is the requirement of the interconnected world. One piece of engineering manufactured in a factory may require different components coming from different parts of the world. It's very important that people talk the same language or at least understand the same language. This would not be necessary several years ago when civilizations were somewhat isolated from each other, and in one civilization if the length of the foot of a king is called foot, then in another civilization something else could be used to measure the length. In physics, systems have evolved over a period of time, and the recent system is the SI system. In SI system, whenever we talk of length, we talk about meters. Whenever we talk of length, we talk of meters. We have to understand foot also, but foot is not there in the SI system. Some things don't go easily because of historical reasons. In some countries for length, large length, they use miles, and in some countries for long length, they use kilometers. In some countries to measure the volume of petrol, they would use gallons, and in some countries they would use liters. Things which are historical in nature don't go so easily. So that is fine, but there has to be a standard system that everybody instantly comprehends. So when we say 1 meter in any part of the world, it means exactly the same thing. We have physical quantities which are fundamental physical quantities, and there are other physical quantities which are derived physical quantities. For example, if I say that length is a fundamental quantity and time is a fundamental quantity, then velocity I don't need to take as a fundamental quantity. If length is fundamental quantity, if time is fundamental quantity, then magnitude of velocity is the length upon time, right? Length upon time. So I don't need to call that as a third fundamental quantity. It is a derived quantity once you have defined length and time as your fundamental quantity. So the bare minimum quantities that are required so that you can get any other quantity as derived quantity. The bare minimum number of quantities so that all other quantities can be derived. They are the fundamental quantities. Once you have defined these fundamental quantities, you can get any derived quantity. Velocity was one example. Force could be another example. Torque could be a third example. Electric field could be the fourth example. Magnetic field could be the fifth example. We don't have to call any of these as fundamental quantities, because once we have defined fundamental quantities, all of these, electric field, magnetic field, electric potential, electric resistance, moment of inertia, torque, work, power, all of these can be derived easily. Now there has to be an agreement internationally. World is interconnected now, so everybody should be able to speak the same language. So there should be an agreement that everybody agrees that, okay, these will be called the fundamental quantities. Because if somebody says that length and time would be fundamental quantities, and therefore velocity would not be fundamental, it would be derived quantity. Then somebody else from some other part of the world may say, no, I will take velocity as fundamental and I will take time as fundamental. So length would be derived. Length would be derived, that fellow says, and I would keep velocity as fundamental, time as fundamental. Now people should not be talking different languages like that. While theoretically it is okay. If you take velocity as your fundamental quantity and if you take time as a fundamental quantity, then you can get distance as a derived quantity, right? Just writing mod of magnitude of velocity equal to distance upon time. So if velocity is known and if time is known, finding distance is no problem. So nothing wrong there conceptually. But one has to follow certain system, and everybody should follow that system because the world is so much interconnected now. A part manufactured is going to be, a part which is manufactured is in one place, it's quite possible it is designed in a different place. So there is an agreement about fundamental quantity. And there are now, at this point, 7 fundamental quantities you can say, or you can say 7 plus 2. I will talk about those 2 also. But let's first talk about these 7. Length is, yes, one of them. Length is one of them. In fact, mass, length and time, these are there since long. Mass, length and time. And then science evolves over time, and then some refinements have to be done here and there. So yes, I'm coming to that. But first we talk about length, we talk about mass, we talk about time. Now when I say these are fundamental quantities, let me also talk about their units. Now just saying length, what length? Now how long is this? There must be an agreement of the unit also. Somebody can talk about length of pen in kilometers, right? And somebody can talk in centimeters. Or let me say inch and centimeter. Probably they make more sense, inch and centimeter than kilometer. So inch, centimeter, foot, meter. There has to be some standardization in the unit also. So physical quantity also, which should be the fundamental physical quantities, and what should be their units. What should be their units? So for length, meter is the one which is agreed upon. So you can't stop people using foot, especially in a place where it is originated. People would be fond of using foot. So that really will go with time, but there is a standardization that length unit, meter. Standard unit is meter. And then talking about mass, for mass it is kilograms. People would still use grams. Sometimes it is convenient also to use grams. In fact, sometimes it is convenient to use foot also. Sometimes meter would sound too big, so foot would sound more convenient. So as far as standard units are concerned, for length we have meters, for mass we have kilograms, for time we have seconds. For time we have seconds. Many times it is convenient to talk in hours, many times it is convenient to talk in minutes, but the standard unit is seconds. Now these 3 are there since long. Then as there in the message current, electric current. Electric current is a fundamental physical quantity and its standard unit is ampere. Standard unit is ampere. And then we have temperature. For temperature it is not degree centigrade, but for temperature it is Kelvin. Yes, you have seen in chemistry how we talked or how we introduced Kelvin from Charles' law, where we extended the graph and where we saw it cut the x-axis. So that is the one, Kelvin. Kelvin is the standard unit for temperature. Then very important is the amount of substance. Amount of substance, yes, moles. Especially in chemistry, and moles is, in fact in chemistry you know how important mole is. And then we have luminous intensity. Luminous intensity has to do with light, and that is a fundamental physical quantity, luminous intensity, and its unit, yes, unit is candela. Its standard unit is candela. So these are 7, but there are 7 plus 2. So 7 fundamental, you can say these 2 are the supplementary units. And these 2 supplementary units are both angles. And both angles, when I say, one is the planar angle, other one is the 3-dimensional angle. Planar angle is very easy for you to visualize. It can be shown on the board very clearly. And this planar angle is measured in radians. It is in radian. Unit is radian, not degree. You can understand the importance of radian. You can understand why in trigonometry we have emphasized so much on radians. When we talk in 3 dimensions, then the angle which is involved, for example, you can visualize a cone. Now showing cone on 2-dimensional region is somewhat more difficult. So you will have to visualize that what I am drawing is actually a 3-dimensional figure. I will try to show it by constructing an ellipse, that this is the cone. This is the cone. Now, you might have come across the drawing of cone in 2 dimensions, like when you learn mensuration in earlier class, then you do learn about volume of a cone, and you see the figure of cone, and probably you talk about this angle also. But that angle, if you have talked about, that is not the real angle as far as cone is concerned. That is the projection of a 3-dimensional figure on a 2-dimensional plane. Like what I have marked is the 2-dimensional angle of the cone. How can that be the real angle? Take an ice cream and see how that angle looks like. That's a 3-dimensional angle. So that 3-dimensional angle is called the solid angle, and we will talk little about solid angle in this whole course. Not so important, but it is used in some cases, like in case of Gauss's law, there can be some mention of solid angle. Solid angle is measured in steradian. So 2-dimensional angle, radian. 3-dimensional angle, steradian. So these are the 2 supplementary units, right? So we have 7 plus 2. Many times, now as I mentioned earlier, if I am talking about the length of the pen, while I can talk in kilometers, it doesn't give a feel. You can't picturize immediately when you hear that pen is so many kilometers long. You understand it better if somebody says so many inches long or so many centimeters long. To handle this type of problem in science, we have certain powers of pens used. For example, Angstrom, when you hear, Angstrom is what? It has to do with 10 to the power minus 10 of meter. So, when we say, we want to say something very small, wavelength, in both model topics we have seen the wavelength coming in nanometers, nano. That's what I'm talking about, powers of 10. If you want to say something very small, you can talk in terms of nano or micro. Micro of anything would mean 10 to the power minus 6 times that. So that's small. If you're trying to measure even smaller, like wavelength, you can go for nano, 10 to the power minus 9 of anything. You are dealing with even smaller amounts, like in capacitance it happens. In fact, in capacitance, all these happen, 10 to the power minus 6, micro, nano, pico. Pico is 10 to the power minus 12. And then if you want to go up to the nucleus level, size of the nucleus, then 10 to the power minus 15. So, we have some word for each of these and more. Micro, nano, then pico, then femto. Now, interestingly, when we talk about 10 to the power minus 15 meter, it is called Fermi. When it is meter, it is called Fermi. But 10 to the power minus 15 can be used with anything. So, in that context, it could be femto. There are more, not just these 6, 9, 12, 15. And how about the other side? We are talking about big numbers. If you're talking about big numbers, then 10 to the power 3. 10 to the power 3 is kilo. 10 to the power 3 is kilo. Then 10 to the power 6 is mega. 10 to the power 9 is giga. And then you just keep on going on that side also. And these you can use with all sorts of different units. We talked about the fundamental quantities. We talked about the units for these fundamental quantities. We talked about how to modify them to sound small, to sound big, both. As far as derived quantities are concerned, most of the quantities will be derived quantities. I took a simple example of velocity. Velocity's magnitude is distance upon time, let's say. So you can easily derive that with respect to the two fundamental quantities, length and time. Talking a little bit beyond that, how about talking about force? Now force is mass times acceleration. Force is mass times acceleration. Mass is a fundamental quantity. No need to touch that. Acceleration is a derived quantity. So that needs to be converted to fundamental quantity. So that is length upon time square. So derived quantity is obtained in terms of fundamental quantity. There can be more and more complex examples, and they all can be handled by just following this type of procedure. Keep on solving till you have only fundamental quantities. These things like meter, kilogram, seconds, ampere, all of these are clearly defined. Definitions you would find in textbooks. I am going into the concept. Definitions can be seen in textbooks. But you would find that they have very clear definitions. This is how 1 meter would be called. And that's very important because, as I said, different people collaborate with each other, different countries collaborate with each other. They collaborate on very accurate things. Let's talk about satellite, where you need many decimal places accuracy. So these definitions need to be very clear, and not just definitions. You would find that 1 meter rod, the most accurate rod, that is there with every country. That is the most accurate meter you would find. And what you find with in some markets, etc., that meter is okay. That would not be as accurate as that meter I'm talking about, because if you look at the ordinary meters, then it will have the effect of temperature. Ideally speaking, there should be zero effect of temperature as far as length of a meter is concerned. So that meter stick which is there with every country, that should be made of such a material which has absolutely minimal effect of temperature expansion and of other things in the surrounding. Meter is just one example. Second is very clearly defined. And likewise, other things are very clearly defined, and countries have these measurements with them so that everybody gets it the very same. Let's now talk about dimension. What do we understand by dimension? As I said, most of the physical quantities are derived quantities. When you are trying to derive a quantity, you are trying to get it in terms of fundamental quantities. And the concept of dimension helps you in that process. For example, force. Supposing I do the same thing in short. I write Newton's second law, F equal to ma. And then realizing that m is already fundamental, I don't touch it. And then I focus on acceleration, length upon time square, L upon c square. You see those capital fellows? Short. And then finally writing it as mLT minus 2. mLT minus 2. The exponent of the base quantity, look at m alone, the exponent of the base quantity that enters into the expression is called dimension of the quantity in that base. Dimension of that quantity in that base. So here we find that dimension is 1. The exponent is 1. For L, exponent is 1. For T, the exponent is minus 2. That is the story for force. To make it very clear, I am writing down here what are the dimensions of force if that is asked from you. Do what I have done and just look at the powers. Dimensions of force are 1 minus 2. But 1 in what? 1 in mass, 1 in length, minus 2 in time. So you would say dimensions of force are 1 in mass, 1 in length, minus 2 in time. Mass, length and time, these are the things that you would see most often. If you are wondering that we have talked about 7 plus 2, what happened to the rest? Well, it is just that force does not depend on ampere. Force does not depend on ampere. That's it. So, what about others? Everybody has got 0, 0, 0, 0 exponent. MLT minus 2. If you like, write a to the power 0, ampere to the power 0. Write for others also if you like, but what's the point? It is understood that if you are not writing others, then they all have got power 0, 0, 0. So that's about dimensions. It is especially useful when we are talking about derived quantities. Now, there is something called dimensional formula also. Dimensional formula also. If you write force as MLT minus 2, then that whole thing, MLT minus 2, that is called the dimensional formula. And 1, 1 minus 2 are called the dimensions with respect to mass, length and time respectively. Any questions about fundamental quantities, derived quantities, dimensions, dimensional formula if you have, then let me know or we proceed further. Very well. I'll try this simple problem. Suppose I tell you that there is something called energy, and that energy is given by half mv squared. Then can you tell me the dimensional formula for energy? Dimensional formula for energy. That's very quick and correct.
ml to t minus 2.
Yes, I could hear that
t
also.
minus 2.
Yes. ml squared t minus 2. Right. If anybody has any questions regarding this, let me know. If you would like this to be discussed on the board, then raise your hand. Fine. Let's make it more difficult then. You certainly know about Newton's law of gravitation. So you know what G signifies. Okay, let me not write even the equation. Without that, let me ask you, if you find it difficult, I will do it. What is the dimensional formula of that G which is used in Newton's law of gravitation? That's quick. Let's see. -1 cube -2. Yes, that's correct. Fine. And now if anybody would like this to be discussed on the board, then you can raise your hand. Okay, here we go. From Newton's law, F equal to G, m1 m2 upon distance square. That means G is F d square upon the m1 into m2. Force we have already discussed, so I'm just copying this, mlt minus 2. D, distance square is L square, mass is m, another mass is m. You can treat them like numbers. That makes it so easy. Treat them like numbers, like cancelling these two fellows. So then that m would go up, this m would go up. We have m minus 1 L 1 plus 2, making it 3, and then t minus 2. If you have any question regarding this, then just let me know. Well, now some equations you may be knowing, but many equations you may not be knowing at this point of time. So I may have to give you those equations, and then you can do working on those and tell the dimensional formula, etc. You may not be knowing some physical quantities also at this point. Nothing to worry. In those cases, you can always ask. Let me just talk about one thing, one physical quantity called surface tension. Surface tension is a property of, let's say, water, to make it simple, that its surface is stretched. Its surface is stretched. And you can see that mosquito can land on the water surface. Water has property that its surface is stretched. Not only water, even others, but water is a simple example. And surface tension is defined in certain way. Surface tension, generally when you hear the word tension in physics, if you have done little extra in your earlier classes, then you probably know that tension is force. But in case of surface tension is not a force. It is defined in a particular way. So either I give you that definition and then I ask you to find out the dimensional formula for surface tension, or I give you some other mathematical relationship involving surface tension and then I ask you to find its dimensional formula. There can be many approaches to finding dimensional formula. Consider this problem that we discussed some time back, that half mv square problem. Anyway, I hope you remember it. We discussed energy problem half mv square. Energy is possible to obtain not only by using that formula. That formula incidentally was for kinetic energy. Energy does not have to be kinetic always. Energy due to height is not kinetic energy, but it is the potential energy. So, to find the dimensional formula for energy, one approach could be to use half mv square, kinetic energy. Other approach could be to use potential energy, which is mgh, potential energy. There can be a third approach, that Einstein's energy formula. What is that? Energy equal to mc square, right? So yes, so half mv square, kinetic energy, potential energy, mgh, then that mass to energy, Einstein's formula, mc square. Then how about what you have learned in chemistry, energy of a photon? How much is that? H times nu, times constant multiplied by frequency. Maybe one of the hard ways to approach is to use H nu formula. Easier ways is to use half mv square or mgh or mc square. Not only these four formulae for energy, there are several formulae for energy. So any of these formula can be used to find the dimensional formula for energy, or even definition can be used. Suppose I tell you that energy has to do with work. So now what definition can be used? So many ways to approach the very same problem, the dimensional formula of something. For surface tension, the easier approach is to tell you the definition. If I tell you the definition, you can give the answer in no time. Suppose I tell you the definition, raw definition, not very refined. It is the force per unit length. It is the force per unit length. Then what could be your answer for dimensional formula for surface tension? That's correct. Mt minus 2. Mt minus 2. So when we say force per unit length, it is mLT minus 2 upon L. And that is mL0 T minus 2. That's an easy way to find the dimensional formula for surface tension. A refined definition would not just say force per unit length. It would say consider a liquid surface, draw an imaginary line. It will talk all those things. But for dimensional formula, it's good enough. But there can be a harder way to get the same result also. Supposing I tell you some relationship of surface tension with some capillary tube of some height h, of some radius r, then this way also you can do it. Rho is the density. Rho is the density of the liquid, and r is the radius of the tube. Height h is the height of the tube divided by 2. Constant plays no role when you find the dimensional formula. Using this, can you find the dimensional formula and see if you get the very same answer? You are getting the same. Okay, if anybody would like this approach to be discussed on the board, then raise your hand. Okay, here we go. Density. Density is mass upon volume. Can you tell me what would come in place of volume? What would come in place of volume? Correct. So putting m by L cube, g, that's just acceleration. Acceleration is length upon time square. So length upon time square. Then radius is of course length, and height is of course length. And now you can see L cube gone, and you have n t minus 2. If you have any other questions, just let me know, or let me introduce you to another physical quantity. Alright, here we go. The next physical quantity is thermal conductivity. Thermal conductivity. What's the idea? If you, on a hot day, just outside, under the sun, if you keep a stone, let it be there for some time, stand on it barefooted, you know what would happen? On a sunny day, summer sunny day, outside, under the sun, place a stone. Let it be there for some time under the sun and then stand over it barefooted. You can imagine what you would experience. Just near that stone, keep a wooden block also. Exactly the same geometrical shape. And stand on that wooden block and see what happens. You also know, I think, what would happen in that case. You would feel much more comfortable if you are standing over a wooden block in comparison to standing on a stone. Even though the floor temperature is the same, even though the bottom temperature is the same, the top, you are standing on the top. When you are standing on the top of a stone, you feel quite uncomfortable. When you stand on the top of wood, you feel quite comfortable. Thermal conductivity. You have, you have learned about electrical resistivity in class 10th part, electricity topic. Electrical resistivity, rho, that you have learned about. Just opposite of that is conductivity. So one can talk about conductivity in case of electricity. One can talk about conductivity in case of heat. Some materials conduct heat very nicely, and some materials do not conduct heat nicely at all. It's a material property. So this is a physical quantity we are talking about, thermal conductivity K. Now you can find the dimensional formula for thermal conductivity if you are given some information about it. Some mathematical expression if you are given, you can tell. Here is the mathematical expression. Q is K times area of cross section. That stone or that wood, the cross section of that, then temperature difference. If temperature difference is more, better heat flow would take place. theta denotes the temperature here. If you like, I can replace it by T. T for temperature perhaps will sound more comfortable. So temperature difference is T2 minus T1 is temperature difference. D is the you can say thickness of that stone or thickness of that wood. T is the time. T is the time. Time, thickness, area of cross section, temperatures on the two sides, and K is the conductivity. Q is the heat. Q is the heat. And what is heat? Heat is energy. Heat is energy. There are some quick, okay, LKT. There are some quick answers. Let me check. Well, I think you may have to recheck your working. I hope you have taken Q for energy. Energy is energy. Kinetic energy, dimensional formula for kinetic energy you can use for Q. Now you can raise your hand if you would like this to be discussed on the board. Okay. K is given by QD upon A, T2 minus T1 into time. Energy. What did we find for energy? Dimensional formula. Energy dimensional formula was how much? Half mv square mass L square T minus 2. ml square T minus 2, I suppose. Right? ml square T minus 2. And D is the distance, so L. Area is length into length. When you subtract two temperatures, you get temperature, right? When you subtract two temperatures, you get temperature only. K, sine, capital T. But then I hope this T does not confuse with that T. I think I would go back to theta only. So L square, it's like just cancelling the two. L to the power 1, T to the power minus 3, K to the power minus 1. Yes. That's right. If you have any questions about this, then just let me know. Okay. We stop at this point.